Hi, welcome everybody. This is the breakout session called Microsoft Research and Visual Studio. My name is Wolf. I'm with Microsoft Research in Redmond. And we're going to be presenting two extensions for Visual Studio today. And this is a two-part talk. I'm going to do the first part, and I'm going to be talking about ImageWatch, which is our Visual Studio extension for debugging C++ image processing code. And then in the second half, my friend Francesco is going to take over and tell you about the Smart Programming Assistant, which is a really cool plugin for Visual Studio that does real-time static code analysis as you're typing. So it basically finds bugs in your code as you're writing them. So make sure to stick around for that as well. OK, so let's start with the first one. This is all about image processing. And so we all have camera phones now. We take lots of pictures. There's lots of images around these days. And so there's also a lot of code that processes these images. And there's also, needs to be maintained. There's still apps to be written. And the typical examples would be, your photo editor where you load an image and you apply a cool effect. Or there's the whole augmented reality space where you have a live feed from your phone camera and you're overlaying something on top of it. And so the common architecture that underlies all of these applications is you have some sort of a image processing pipeline. It starts with your input image, and then the input image undergoes a couple of transformations, and in the end you end up with whatever result you need. And so here's two examples of what these pipelines may look like. So at the top, so this would be for the image effect in your image editor. You start with the input image. Then maybe you remove the noise of the image, and then at this point you have a denoised version of the image. And then maybe there's another step that increases the saturation. So now you have an image with more saturation. And then this pipeline may also branch out and come together in the end, in this example, for like a sharpening operation or something like this. And the example for a face for the mustache cam is sort of similar, right? So the key data structure in all of this is an image, and it could look something like this in C++. It's a struct myImage, and it has a pointer to some pixels, and it has a width and a height. Here I call them number of columns and number of rows when you think of it as a matrix. And it may also have something like a format bit field that tells you what kind of what format the pixels are. Is it an RGB image? Is it floating point? Is it 8-bit? Is it it could be depth if you're working with a depth sensor like the Kinect. It could be anything. It could be probabilities, whatever. And of course, things are going to go wrong every now and then, and you'll see things like these on the right here. So maybe this looks like uninitialized memory or something, or something more sort of semantic, more like this down here. And because these pipelines tend to be pretty long in non-trivial applications, it's not clear where the error comes from. So what you need to do is you need to get back to the beginning of the pipeline, start with the input image, and then track it through every single operation. And after each operation, sort of validate the state of your program. Now, the thing is, with image processing, your program state, that's your pixels, and there's millions of them. So there's really no good way to do this unless you visualize these intermediate images. Right? So you want to look at the denoised image here, and then you want to look at the saturated image here, and so on. And here's a way how to do this. You could call it printf debugging or printf style debugging. So imagine this is your pipeline. It has two processing steps. Right? It takes an image here, then it processes it, produces image 2. It takes image 2, processes it some more, produces image 3, and returns image 3. Now, if you wanted to debug this, you could put code like this in here that essentially dumps the program state into an image file before and after every step. And then you run the program, and you open these files in your favorite image viewer and find the bug. And this works, but if you do a lot of this, it becomes very painful. And when you think about what you need to do now, you have to now work with two different applications. You have your IDE, and you have your image viewer. You have to switch back and forth between them. Also, you have to over and over modify your code because you don't know maybe where to start. And so you sprinkle a couple of these save image instructions here, and then you run it. And, well, maybe all the images are OK, so you remove this again. You put them elsewhere, and then you run it again, and so on and so forth. And then also you have to start worrying out multi-threading, because if you can't like save an image from a code path that is called from 2 different threads. So that's why people start actually writing libraries around this. So they write debugging libraries that you link to your code in order to debug image processing problems. And because we're a devices company, we want to run this on devices like our phones and tablets. And so remote debugging has become a whole new interesting thing that happens a lot. And if you're remote debugging, you can't just save temporary images to your temp folder. You have to save it to isolated storage. And then when you're done, you have to download it from your device. And of course, in the end, you have to remember to remove all these statements from your code, because in the best case, if you forget to do it, you have a perf problem. And in the worst case, you have a security problem, because you're dumping internal information to your hard drive. So to make a long story short, what we really want to do, we want to use Visual Studio's amazing built-in debugger to look at images, right? So we want to be able to put a breakpoint, let's say here, and then hit F5 in Visual Studio, and look at the watch window, and then see, oh, there's image 1, there's image 2, and these are the values, and so on. But of course, Visual Studio will only show you values as text, right, not as images. And so this is why we wrote Image Watch, which is a plugin that gives you a new watch window. So it doesn't get rid of the old one, it just gives you another one that shows images. And it looks like this. And so one thing I wanted to point out here is there's 2 sides. There's the left panel and the right panel. On the left panel, you see a list of all the images that you're watching right now. And they come with a friendly description, like the size and the pixel type and the underlying C++ type that this object has, right? So in this case, image 1 is a myImage object, and this is the size, and this is the type. And it also comes with a thumbnail. And then when you select one of these in this list over here, you can view them in detail on the right, and you can zoom in, and I'll show you in a second in the live demo how that works. And then I also wanted to point out this one thing up here. There's a radio button that says Locals and Watch. And so if you've worked with Visual Studio before, you know there's different types of variable windows when you're debugging. There's an autos window, a locals window, and a watch window. And this simply means that we've lumped together the locals and the watch window into one tool window, as they call it in the extensibility framework, so that they move around together when you dock them in different places and so on. So let me switch to the demo. Okay. So this is a simple Windows Store app that I wrote to demonstrate how the Image Watch works. And let me first run it one time so that we see what it's doing. So I'm running it. Sorry, it's a little bit cropped because of the resolution. So there's not much going on here. There's a big test button at the center. And then there's an input image and an output image here. So when I hit the test button, what happens is I load the build logo from a file in the app assets. And then I run it through a pipeline that has 2 steps. In the first step, it just inverts all the colors. So that's why blue becomes orange and white becomes black. And then in the second step, I just flip the image upside down. Okay, so that's all the app does. And so this is what it looks like in code. This is a XAML app. I'm not going to show you the XAML, though. What's interesting is here in this folder called Image Processing. Can you read this okay? So there's a folder called Image Processing. This is where all the C++ code lives that I use to process images. And so here in myimage.h, this is a definition of our image type. So it has a width and a height, or a number of columns, number of rows. And it has a std vector that holds the pixels. And there's also 2 declarations for the function that I'm going to call. One's called invert colors. The other one's called flip upside down. And then here in pipeline.cpp, that's where you actually call them. So this is the function that gets called on my blue build logo when I hit the test button. And so when I hit F5 in Visual Studio now, the program starts in the debugger, and I hit the test button. And because I put a breakpoint here, we're now returning to the program. And here on the right, you can see Image Watch in action. And you can also see it's in locals mode right now. So in the list over here, you see all the image variables in your current scope, right? And when you compare this to the locals window here in Visual Studio, it's the same variables. But if I go up one frame in the call stack by double-clicking here, you can see that, sorry, I didn't want that here. You can see that there's 5 local variables here, but only 2 of them are images, and ImageWatch only shows the images, of course, right? So I go back to the instruction pointer. Now, you also notice that the first image has a thumbnail and the other 2 don't. And that makes sense because the other 2 actually don't exist yet. The constructor hasn't run. But when I single step over this instruction, you'll see that image 2 appears. And then likewise, when I step over this instruction, image 3 appears. And when I select one of these images in the list, I can view them in more detail over here. So I can zoom in and pan around. And when I hover my mouse over here, you can see the X, Y coordinates up here. And you can see the color values here. So here we have 4 color values because the image format is BGRA. That's blue, green, red, alpha. Okay, so white, for example, is all 255s, and blue is a lot of blue, some green, no red, and its opacity is 100%. That's why alpha is 255. And so one thing that you want to do over and over again is you want to compare a particular pixel or a particular region in an image between, before and after an operation. So for example, in the invert colors function, I want to see what happened to these pixels here between before and after this operation. And so what you can do in ImageWatch, you can link these zoom levels together. So I right-click on the viewer here and I say link views, and from that moment on, all images that have the same size as the one I'm working on right now will share the same zoom settings. So when I switch over to here, you'll see the same region. And so when I pan around like this and go back, so that they will be linked. And if I don't want that anymore, I just uncheck this, and then they'll zoom independently again. Now, there's also the watch list over here. So this is the watch window now, and this is where you, just like in Visual Studio, you manually add and remove images, right? So I could write image 1 here, and that's image 1. This works with values and pointers, and actually you can type any expression here that evaluates to an image. So, for example, I could write address of image 1. It's the same thing. The only difference is that now it actually shows that this is a pointer to a const, my image, and not a reference to const. Right? And there's another way to add images into here through the UI, which is these little magnifying glass buttons here. So as soon as you installed ImageWatch and enabled these types, which I'll show you in a second how that works, these magnifying glasses will show up. And they will show up in the normal Visual Studio window. So here, if I click on this, it says add to ImageWatch. Then your image is in here in the viewer. Same thing in the debugger data tip, which is this tooltip that shows up when you hover over a variable in your code window. Same thing, I can click on here, and I put this into the watch list. Okay, another thing that we added to the watch window is that you can apply simple operations to the image directly to help you, visualize your data. So you can do things like extract a single channel from this image 1 image, right? So for example, if I wanted to extract the red channel from that image, I use the band operator. That's how we call the one that extracts a channel or a band. And I say image 1, and then 2. 2 is the zero-based index of the red channel in this 4-channel image. I hit enter, and then you see, so this is now an image of type operator because it's not really an image. It's something that you created because you wanted to, get the red channel out of that image. And it's a 1-channel image, and it's black and white because that's how we, by default, display 1-channel images. You can also use pseudo colors here if you want. And that brings me to the help button. So we have an online help document that you can get to by clicking on this button here. And it describes all of ImageWatch in great detail, including the operators. So this is how operators work. Can I zoom in here? Oh, yes. It also lists all of the operators that we currently have. So there's the band operator that I just showed you. There's also thresholding, clamping, there's absolute value, scaling. There's a pixel-wise difference. If you have two images, you can diff them and look at the difference image. We also have a file operator that lets you load let's say if you have a reference image on your disk, you can load that reference image and then compare. And there's also a mem operator, which is sort of you can point it at any address in memory and say, well, display those bytes as an image. And of course, you have to provide all the metadata in this one. You have to say what's the pixel type, how many channels, and so on. Okay, so I have another demo I wanted to show. It's a very quick one, and this involves a Windows Phone. And so in terms of the image processing, it's exactly the same what we've seen right now. It's the same pipeline. It actually shares the same code. The only difference is that now we're grabbing frames from the phone camera and feeding them into the pipeline. So let's see if I can get this to work. So I'm running this under the debugger, and I'm pointing the phone, the audience, over here. So this takes a while. Okay, so now we're at this breakpoint, and you can see this is those are the 3 reserved spaces here. So this is the frame that just came from the camera. That's image 1, and invert colors ran on this one and produced image 2. So image 2 is the same thing, but with inverted colors. And when I step over this, we get image 3. And because it's actually good I have this invert, because I held the phone upside down. You can imagine this is, as I described earlier, this is much harder to do if you're trying to dump all these images to disk and so on. Because what we're actually doing here is we're reading memory from the phone in real time through the USB cable, and you could step through disassembly here and do the same thing. So after every step, you would get the update in real time. And so this is a nice thing about Visual Studio's extensibility, right? So you can write a plugin like this, and it will just work across all the devices and give you the same experience no matter where you run your code. Okay. So that concludes the demo. Let me go back. Which number is the 1? Thank you. Okay. That was the demo. So now in this last part of the first part, I wanted to talk very quickly about how you can use ImageWatch to debug your own image types. Because the thing about ImageWatch is you can essentially register any C++ type that is an image in ImageWatch, and then it will just work just like the My image we just looked at. And so to make that work, you need to do 2 things. You need to tell ImageWatch first that, let's say, if your image is also called My image, that My image is an image, right? So you need to tell it the type. And then you also need to tell it that now, given a reference or given an object of this type, what is the C++ expression that gets you at the width and the height and the pointer to the pixels and all the metadata that you need to actually, read the memory from the running app and display the image? And thankfully, this is not too hard because Visual Studio already provides a mechanism that we can piggyback onto, and it's called NatVis files. And if you've never worked with this before, NatVis is short for Native Visualizer, and it's Visual Studio's way of they let you customize how Visual Studio displays values in a debugger. So and it works like this. Let's say you have this My image object in your code, and you somehow want to customize the way it looks like in your locals window. So what you do is you write a little bit of XML, and this is the NatVis file. So you say type My image, so that says, okay, we want a special visualizer for My image. And then you add these items here to this list, which basically say, well, I want to evaluate this member expression here and calls, and I want to display it as width. Or I want to take n rows and I want to display it as height. Or I want to take pixels._my first and display it as data. So pixels._my first is in the std vector, which is what pixels is. It's just the data member that points to the first element in the vector. So when you look at this in the watch window, you will see this, right? Width, height, and data instead of number of columns, number of rows, and pixels. And so this is what we leverage in ImageWatch by basically defining a set of a set of keys that we want to see here in the name column. So we parse the name column. We're looking for actually for width, and we're looking for height, and we're looking for data. And there's two more that I haven't mentioned that describe the format of your pixels. And so you can take any, as I said, you can take any C++ structure you want, as long as you can write a NatWis that has all these properties in the name column. ImageWatch can display them. Okay, and so we've done this for you for types that we know people are going to use all over. So now, for example, OpenCV. I don't know how many of you have heard of OpenCV. Okay, quite a few. Yeah. So OpenCV, for those who don't know, is probably the most widely used open source computer vision or image processing library out there. It's a C++ library, and it's been around for a while, and so it has actually at least 4 different image containers that it uses. So this is an old one. This is actually a C struct from back in the day, and there's also a template version of their containers. And so we've written these NatWis files for all the OpenCV types. So if you install ImageWatch today and you use OpenCV, then it will just work out of the box. And so we've also started to work with teams inside Microsoft to give you visualizers for ImageWatch for Microsoft image types. And so coming in Visual Studio 2013 RTM, which unfortunately is not the preview that you got here at Build, but it's a couple, I don't know when it's going to come out, we will have visualizers for writable bitmap in WinRT and also for the 2D media foundation buffer. So if you're working in that space, you can use ImageWatch and it will just work. Yeah, so if that's something that interests you, please go ahead and give it a try. ImageWatch is available on Visual Studio Gallery. It works with Visual Studio 2012 and 2013 preview, and it's free. And it's if you've installed extensions before, you know that this is a very simple process. It's a single click, it installs, it's there. If you don't want it anymore, it's a single click, it's gone. Yeah, and I think that concludes the first part of this talk, and I think we have time for questions. Thank you. No, sorry, let me just repeat. Yeah, the NatWis, do you have to put it in your code? No, I'm sorry, I missed to mention this. So what you do with the NatWis, you copy it into a folder that Visual Studio knows. So it's this folder here by default. So you copy it under My Documents, Visual Studio 2013, Visualizers, and then you can give it any name, .natwis, and Visual Studio will just pick it up. Yeah, good question. Yes?
RGB format is, just to fill this out, I presume the RGB format is like the next thing that would go on the right there so that you know.
Yes, exactly. So, and this is described in great detail in the online documentation for ImageWatch. And we support a number of formats. We support RGB and BGR and YUV and then grayscale and so on and so forth.
Okay.
Yeah. Yes?
C#?
I'm sorry. I know, yeah, C#. We get, the question was C#. And it's a good question. So, I mean, the thing is, like, we first built this for native code because we write a lot of image processing code at MSR, and yeah, I don't know if you'd like to hear this, but like, because of, I don't know, maybe historical reasons or performance, we write, that's often written in C++, right? And so that seems sort of the most straightforward thing for us to do. And then, you know, we added things like the NatWis mechanism, and that's obviously for native, so it would be non-trivial to make that work for C#. Although I guess, yeah, I mean, it could be done. It's just like, and I know that, yeah, the question keeps coming up. And yeah.
Is the source available?
No, it's not. Sorry?
Can you repeat the question?
Oh, yeah. Oh, sorry. Yeah, the source code is not available. Yeah. I'm sorry. Yeah. Okay. If there are no more questions, I'll hand the stage over to my friend Francesco. Yes.
So thank you, Wolf. Okay, here should be as easy as changing this one. Ooh. What's happening? Yeah.
Oh,
Okay, I have to open my microphone. It's open. Can you hear me? Yes? Okay, so thank you, Wolf, for the introduction. And now I'm going to talk about the Smart Programming Assistant. I'm Francesco Logozzo. I'm a researcher at Microsoft Research in Redmond and in the software engineering group, RISE. And as you can understand from my funny accent, from my red shoes, for those of you who can see them, and from my T-shirt, I'm Italian. So in this talk, I'm going to hand wave a lot and say stupid jokes and move a lot. So I hope you will not fall asleep. So what is the Smart Programming Assistant? So the Smart Programming Assistant, it's a vision we have been developing with my friends and colleagues at RISE for what programming should look like, what is the future programming. And essentially what it does is that it gives you a real-time feedback about your code. In particular, it performs a deep semantic analysis, static analysis, and it finds tricky bugs in your code and also regressions. But it does not stop here. It does not only say, oh, look, this is wrong, but also helps you how to fix your code. You can fix your code by adding a new specification, better specification, or fixing your code. Now, how this works? So I have a couple of slides before going into the demo, so please don't fall asleep. So the demo I'm going to show you is based on two main pillars, very stable tools. One are code contracts. So how many people knows code contracts in the audience? Oh, there are a bunch of them. Good. So I'm one of the author of code contracts with my friends Mike Barnett and Manuel Feindrich. So I'm happy at least someone knows about them. So what are code contracts? Code contracts have been introduced since version 4 of .NET as a way of specifying precondition, postcondition, and object-oriented and object invariants in your code. And there are a bunch of tools that you can go and download right now on Visual Studio, which makes use of these contracts. They make use of this contract to automatically generate your documentation, to perform a runtime checking so that you have essentially testing on steroids, you test more things, and to do static checking so that you can verify your code is correct statically without running it for every possible execution. So this is one of the pillars of the demo you're going to see. And the other pillar is the Roslyn CTP. So Roslyn is an implementation of the paradigm of a compiler as a service. So essentially in Roslyn, what they did was to take the compiler, which was a black box, open it, and expose all the stages to the pipeline through an API so that people like me who write tools can use this API and write nicer tools. Very last slide, and then we'll spend all my time in code, I promise you. So the way in which it works is this. We start from the code. So you are there on your Visual Studio, you type your code. And then Roslyn is there, and it creates the AST, and it passes the AST to us. And we perform a strong, very deep semantic inference based on some theory called abstract interpretation, which infers essentially invariants for every single program point in your program. And then it uses this information in order to do a bunch of things. The first thing is to find bugs, so to do error checking, or essentially verifies that your program is correct to say, oh, something can go wrong. And then it does a bunch of other things, as for instance, suggesting you what can go wrong, also tells you you have to add this specification, or saying what it changed since the last version that was good for you. Of course, this thing may not scale. You expect deep analysis can take some time. So what we do for scaling up is that we save the information into a database, so that if you don't change your code, essentially you don't analyze anymore. So this gives us performances. So as promised, let's go into the demo. If we go into a demo, I have to press this magic button as in Star Trek, the first one. So things are changing, and my laptop should wake up. So my laptop is wake up, and yes, you can see the demo. Let's start from a very, very simple example. So what I'm going to do here is that I have some piece of code, some piece of C#, which implements a library function, which inserts an element at the end of a list, which is represented as an array, and then I have some client. So what it does, this class, so this library, it just takes the list, and it updates the element position count, so it's the number of elements in the list, increases counting, and then returns it. So, good. Is this code correct? So, little bit, yeah, I'm asking tricky question, isn't it? So, a little bit of, color things. So, green these green and purple messages that you see are generated from our tool. So green one, it means there is some problem, and purple is this is how you fix it. And when you also will see red, see this is really a bad problem. So what can go wrong here? What can go wrong here? We can go here with the mouse and see what the tool tells. Well, there are 3 things that can go wrong, essentially, in this simple piece of code. It can go wrong that list can be null, and so you get an error. It can be that count is negative, or count is larger or equal to the length of the array. In this case, you get a buffer overrun. So you don't want these things. Now, question is how we defend, what we are doing, what we'll do in order to fix this code. Well, this is a library. So there is not so much we can do. What we can do essentially is we have to notify to our callers, look, there are some values for which I'm going to, to go mad, to do something wrong. So which are these values? And that's what the tool tells us. So it suggests us, but what is even cooler, but yeah, of course I'm not objective, it's that it suggests us and allows us to add those, those advertise this precondition to the code. So for instance, I can add this precondition, and now, as not all of you, unfortunately, are familiar with code contracts, that's the way in which we notify to the caller that we need some constraint on the input. We have to do a precondition. So the contract class is part of .NET, so I can go to the definition. You see, this is part of .NET since version 4.0, and requires. It's the way in which we say, okay, this is what we expect from the caller. In this case, we expect that list should be not null, because otherwise we're going to get definite error. It's easy. And what else we need? Well, we need condition about count. So I say count cannot be negative. So the other precondition is that count should be greater or equal to 0. And you see that while adding this precondition, the warnings go away. So now we are just left with a warning about the relation between count and the length of the array. And let me add the last one. And now the squiggles goes away. I hope so. Yes, it goes away. So my code is perfect, it's wonderful. And let's see what's happened to the client. Oops. Now I get a red squiggle to the client. So what's happening? Well, I have a precondition. This precondition says count should be smaller than the length of the array. And of course, here I'm creating this client with an empty array. I can do it. And then count is 0 because I have no element in the array. So now 0 is not smaller than 0, and both, this is an error. So you see now the squiggle is red. So it's saying this is really bad. This is every single time you reach this program point, you will get an error. So, okay, so what you have to do? Well, I started talking and saying this is a list. I called even my variable list, but actually it's an array. So what I expect in a list is that this dynamically grows. So what we do in this case, we had some code in order to say, okay, let's see. If count is equal to the length of the list, so it means I have no more space, what I'm going to do is that I allocate some array. And what to say, let's do twice the length of this, twice count. And then let me copy all the elements. Let's call array.copy. And now what is the source is the list. And the destination is tmp. And the length, of course, is count. And now let me update the pointer. Say list is equal to tmp. And my code now is perfect, very nice. Isn't it? Oops. No. OK, someone say no from the audience. What's wrong in this code? Why you get this wiggle?
Well, the array would be 0. Well, the caller with 2 times 0 is still 0.
Yes, but there is something else wrong. Why is telling me this warning? So essentially, the new code I introduced, it's dead code. It's just code because of my contract, exact. So I'm asking that count is more than list.length, and then I'm checking if it is equal, how they can be. In fact, that's what the tool is saying. I say, this condition is always, constant Boolean value. So what I should do here is now I have to weaken my contract. I say, now you can call me even when those things are equal. So the smaller became smaller equal. And now, yep, now there is a warning. There's another warning. So now there's an error. So again, the green are the warnings, the purple are the things. So someone already say what's wrong in this code. So even if it was dead code. So there is some problem in this code. And now that I weaken my precondition, now I allow for some other execution. So, and the problem here in this code is that count can be 0 and list.length can be 0. So that's the thing. In fact, that's what the tool is doing. It can suggest it. So actually, how we fix this situation? Now the question is how we fix it. We have this warning. Now the question is how to fix it. So of course, there are infinitely many ways of fixing it. The tool proposed 3 of them. So the first one is to add a precondition. It's one way. Let's see which is the precondition. And this precondition is pretty interesting because it also tells us, so in the case you don't have someone in the audience to spot the bug right away, tells us what's wrong in this code. So what it's saying either count is different from list.length, so it means that we skip the body of the if, and so we are happy. Or, so now count is equal to list.length. Now count should be greater than 0, which is why it is? Well, the problem is because of this guy. Because if it was smaller or equal to 0, well, actually we know that it's equal to 0 because the precondition it says a count can be only greater or equal to 0. So we know that if we ever enter this branch of the loop, and these two things are the same, so count, if this is 0, so we make 2 times 0. 2 times 0 is 0. And then, well, we copy an empty list, and now we get a buffer overrun here. OK. So this is one way of fixing it. Essentially, we are pushing to the code and say, you cannot consider this thing. Or we can do somewhere differently. We can say, OK, let's see for the tool come back. So what we can do is that, well, we can change this assignment, this allocation for TMP. So what we can say is that now, for instance, and you see the tool suggests us, instead of multiplying count by 2, we do 2 times count plus 1. So now the case when count is equal to 0, well, we get 2 times 0, 0, plus 1 is 1. So we have space, and this is OK. And I want to show you one last way of fixing this code, which the tool suggests. OK, let me go back here. And the tool says, OK, suppose that you have some domain knowledge, something that tells you, I know that this code is always correct. The case in which the list.length is equal to 0 and count is 0, it's something will never happen because I know this is things like this. You are right, but, well, I know because I'm a human, I know more than you. Fine. So what you have to do is just tell to the static analyzer, you have to put this knowledge into a static analyzer. And the way in which you do is you add this contract. So you do contract.assume, which think as an assert. The only difference is that the static checker will not try to prove it, will just believe it. And, well, what is the assumption that it says? Say, OK, look, count should be greater than 2 times count. OK, now this is weird. Why is not saying count greater than 0 this program point? Or count different from 0? Any idea? Someone in the audience has some idea? Sorry? Yeah, it requires. But yeah, you may say just count greater than 0 or what's happening. So we are writing real programs running on real machines which have complement 2 representation for integers. And what happens is that if count is very, very large, when we multiply by 2, we get a very, very, very large number, so large that we cannot represent it. In fact, it becomes a negative number. So as we know, a count is greater or equal to 0. So if this guy gets negative, well, the assumption fails at runtime. Say, OK, here you have an overflow, stop. That's the thing. So this is why we get this thing. OK, good. So now I wrote my little library. And yeah, you see also that just want to show you that the client is happy. That, so it just passes the right things. So we are happy. And now we say, OK, yeah, I like this code. It took me so much effort in order to have this thing that makes room. It takes so much effort to make it correct. So I wanted to expose, let's say, as a new API, a new method. So what I do usually is usually I do the extract method. That's what I do in Visual Studio. So what's happening if we do extract method? OK, let's do it. Well, now I'm going to get all a bunch of warnings from the static checker, because the static checker is modular. So when it sees this new method, it does not go inside and see what it's doing. So it can return everything. So in particular, it can return null. And so here it says, OK, list may be null or other things. So that's not so nice, isn't it? So what do we want? So let me go revert back, Control Z. Is actually that when we extract a method, we also extract a method with OK, Control mine, with contracts, because so the static checker gets the contracts for us. So let me show you. Yeah. So yeah, that's pretty cool, I think. So. But of course, again, I'm not objective. So you say, so Francesco, you think it's cool? Yes, it's very cool. OK, now let's look a little bit for these contracts that extracted, just very quickly. They have some interesting properties. They are not trivial. So for instance, what you may expect is that as we were inside the loop body, so what the tool can do is saying, okay, I know what is your invariant at this program point. Let's just take this invariant and make it a precondition. So at this program point here, the invariant will be that count is equal to list.length, which, if you think, is very strong hypothesis for this piece of code. Why should I have count and list.length for the extracting method? This code works, for instance, even when count is more equal than length. In fact, you see the precondition is inferring it's a weaker one. So, nice. Okay, so this concludes the first third of my talk. Now, of course, you say, oh, okay, this is a little piece of code. It's straight line piece of code. So, you don't have loops. Our program has loops, recursion, and these kind of things that makes them difficult. So, okay, I thought, let's consider some piece of code, some algorithm, very, very easy. I think probably it's the second algorithm we are going to implement when we do arrays. So the first one probably is linear search. The second one we implement is binary search. And by the way, just because no one is listening to us, it's just on the internet, this video. I use this as an interview question. So if you ever be interviewed by me, be very prepared on binary search. But no one is listening to us. Okay, so binary search, so it's the second algorithm we do on arrays, and very likely the one we make wrong. So wrong that even professional programmers make it wrong. So how many of you know about this blog from Josh Block? Aware about this blog. So if you are not aware about this blog, well, and the code you see I took from this blog. So you say, oh, I wrote the first implementation of the binary search. I took from this book where there was a correctness proof, very formal, as we are taught at a university. And then you also tested it. So this code was really bulletproof. And then a couple of years passed, and then they started having a bug report about this code. So even professional people, the programmers taking verified code and tested code make it wrong. So binary search is very sneaky, so that's why be prepared for the interview question. Okay, so I took the code, and then I added one bug of my own. So let's start from the bug I added, and then I talk to you about the other bug. So let's go here, the green point. So here the tool is unhappy. It's unhappy because it cannot prove that the array access is correct. So just for those of you, I think no one, but it's good to repeat, who does not know what binary search does? Well, binary search essentially takes an array. It starts from the first and the last element of the array. So it puts 2 points there. Then you take the element in the middle. You say if you found the element, you found it, it returns it, it's happy. Otherwise, it goes on the left or on the right. So you go on the right, on the right, on the right until there's an empty interval. And then you say, OK, I cannot find the interval. So here the tool says, OK, when I'm going and look into my element in the middle, I cannot prove that the index you gave me is in bounds. In particular, it says I cannot find that is about the upper bound. OK, I'm sure you are way better programmers than I am. So who can spot the bug? What's wrong with this code? OK, we can ask the tool then. So believe me, internally, we know there is this link. So there is a link between this green squiggle and this purple squiggle. So from this warning, we generate this code fix. So the tool says, OK, this is the way of fixing the code. And now you see that the squiggle will go away. So why? Well, because we are C# programmers, or at least I am a C# programmer. So what is the first element of the array? It's 0. And which is the last element of the array? It's not the length of the array where I wrote, so that was the bug I introduced. But it's the last element minus 1. That's the last element of the array. So the index of the last element of the array. So, OK, so this was my bug. And what I want you to notice is that in order to infer this kind of fixes and to prove this property, the tool is doing a non-trivial reasoning. Essentially, what it's doing here is discovering loop invariant. You just find a property that holds for all the possible execution of your loop. It's not based on pattern matching as probably other tools of static analysis you are aware of, let's say fxcop or resharper or covariety. This is doing some semantic computation behind. OK, so this was the bug in the binary search on the block I showed you. So the problem here is that when you have very large arrays, very, very large arrays, so the one you get in 64-bit machines, now the last infant soup can get very, very large. So if you don't find a go like this, go like this, like this. And now you get two very, very, very large numbers. Now you have two very, very large numbers. You add them, and you get an overflow. Yes, good. So you get a negative number. That's the bug. And that's wrong. So, of course, now the question is, OK, good. You spot the bug. You know how to fix it? Well, I was nice, so I left my mouse on the fix. But the tool tells you, actually, by default, this is the default behavior of the tool, because otherwise you get too many messages. When it finds an overflow, it tries to fix it, and if it knows how to fix it, it tells you how to fix it. So we can add it, and go on and goes away. Cool. Now, I want to show you just, if you don't believe me, and I think it's not a good thing to believe me, or to believe in general. So what you want is to see some proof. So suppose that I added some condition on the length of the array. So let's say the length of the array should be smaller than some stupid number. Now, you see, we don't see the squiggle for the overflow, because now that I bounded to the length of the array to be 1, 2, 3, 4, 5, 1, 2, 3, 5, 6, there is no warning. But if, for instance, I change the precondition, I say, OK, this thing should be larger than that, now the warning will appear again. See, so this is semantic. That's the message I want to convey you. And very last thing. So on my talk now, I say, OK, Francesco, you've been talking about all these things. And then you say, OK, you started from a code from scratch where you made it correct by construction, essentially. Or you took some code and you changed the warnings. But in reality, we have this huge code basis. Now, what do you have to go to do? So if you ask me, well, the best thing is to go there, annotate with contracts, run the tool, and everything to do. And then will be the wonderful things. But unfortunately, there are only 24 hours in a day. So somehow we have to cope with it. And here I have some simple piece of code. What it does is that it takes, so I want to show, to demo you this situation. What we do in this case is when you have a code base, and essentially you want just to be incremental and use those tools only on the new code, because somehow you believe your old code is correct, because you've been out in the field, you tested it, but probably you're not so sure about the new code. So what you're doing here, say, OK, well, I have this foo, it takes an array of integers. Well, I put my precondition, so I'm pushing to the caller saying, OK, you cannot pass me data to be null. And then I call some external method, some library for which I have no control on it, and I have no postcondition, and, well, I don't know anything about this guy. And I do some check. I say, OK, if this thing is more than the length of the array, then I do reference it. So, well, what the tool does, so at this program point, says, good. I know that data cannot be null because you have precondition. You are checking that the index is smaller data.length, so I cannot overrun on the right. But what can happen is that index can be negative. But you know this is true because for some reason you have some domain knowledge about this code. So what the tool tells you is, say, OK, here you have two options. So let me show you. So the first one is to add a postcondition to this guy, saying that you are returning something greater than 0, but probably you don't have it. Or you can add an assumption. So this is probably the thing you want to do to make it nice, so to document all the assumptions in your code. But again, when you have this big, huge code basis, you cannot go and add all this assumption. You don't want to do it. So what the tool tells, say, OK, instead of doing this and adding the assumption, so documenting it, just go there and let's say to suppress it semantically. So essentially now the tool is storing in the database this assumption. So all the next times, knows that this is not going to happen. And see, the warning went again. Now, this suppression of the warning, what I say is not synthetic. It's not say suppress this warning at this program point. This is semantic. Suppose that for some reason in a new version I write index equal index plus 1. Now, if I write it, you see the warning does not resurrect, even if now all my source code has been moving and pushed down. But suppose that now instead of writing index plus 1, I write index minus 1. And now I have a regression. Now I have a regression because now I'm asking more to this external function. Now I'm asking no more that is greater or equal to 0 as I did in all my previous version, but I'm requiring that this guy is greater or equal to minus 1. So I'm asking more. And so that's why now the tool says, oh, this can be an error. So again, OK, you should fix it. And blah, blah. OK, so I think I'm good with time. I wanted to leave some time for for questions. So I can leave here Visual Studio. So do you have questions, comments, anything else? So please let me know. Yes, can you use a microphone or I will repeat? We can use, I can repeat the question. Yeah,
okay.
Just ask me, I will repeat it.
It's a simple question, but I'm curious on the semantics. When you set the bound, you said, well, this is less than 1, 2, 3, 4, 5.
Yes.
So what is it doing? Is it actually checking the numeric type and saying that this thing is less than, it's sufficiently small that I know it can't overflow?
Yes, so what's happening is, okay, so the question is curious about how it's doing this semantic analysis. So this one. So what's happening here, just to simplify, is that it's abstracting the concrete values that the array.len can take by intervals. So when I'm writing this thing, for instance, let's make it easier. Now, at this program point, the tool will infer that array.length is in the interval 0, 1, 2, 3, 5, 5. Cannot be 6. So that's what the tool is doing. Is get this interval. And then it's propagating this interval here. So for instance, this program point will discover that soup is between 0 and 1, 2, 3, 5, 4, because I do -1. And actually, I'm wrong because it's -1. It's -1 because it can be 0. And then it continues. Now it goes inside the loop of the body, and then it does some fixed point iteration. And at the end, it will discover this program point. So it finds this invariant, and discover that inf is between something, let's say 0, and can be at most soup. So it's 1, 2, 3, 5, 4. At 4, yes, and soup. It's in the same interval. So let me write like this. It's just be faster. So this is what the tool is going to infer. And now at this program point, now it's going to add these two intervals. Instead of doing the addition between integers, it does the addition between intervals. And then it will find that mid is between 0 and this number times 2. And this number times 2, it's smaller than max value, so it can never overflow. That's the way in which it's doing. So it's doing this check. But thank you for the question. It's not so easy, actually, to be honest. It's a very tricky one. Okay, another question.
The opposite of the question that was asked, the guy asked,
Yes.
is this available for native?
Okay, that's good. So the question, now I have the dual question. So I promise in this talk not to use any strange researchy term, no Greek letters or strange formulas, but I have to use the word dual because it's so nice. So before Wolf was asked, is it available for C#? And now I have exactly the dual question, which is it available for native code? And the answer is no, sorry. So the reason is because we are building on the top of Roslyn, so we are using Roslyn. So there is no theoretical reason for which we cannot do it for C or C++ or native code in general.
Compiler engine should be able to provide you the exact same path information.
Yes, if Roslyn will do it, then we'll be happy. Because we are building, remember, we are building on these two pillars, code contracts and Roslyn. There will be some engineering issue probably where you put your contracts when you're in C++, but that's another story. Yes, another question, yes.
Is there a new version of Roslyn that came with this beta version of Visual Studio 2015?
Okay, so the question is there a new version of Roslyn came with this version of new version of Visual Studio 2015? And my answer is I don't know. Okay, so that's.
Is there a way to find out what version this is?
Oh, this one I'm running. Oh, I don't know. I can answer you internally, but that's I go and find it. Yes. So it's a recent one, but it's not the most recent one. I think it's something we pick in March for TechFest, some internal event at Microsoft. Good. There's a question over there. Yes. Okay, yes, there is a question if there is something that shows all the errors. Yes, there is, and so let me see, go here, where is it build, and I have to go to the output window. I always lose the output window. Windows, output, well, actually it's the error window, so view, error list, here it is. So here it is. You see, you get in the error list, so you get, as the compiler puts all its warnings and all its errors, we also had our errors. So this is the list. And actually, if you go on Visual Studio Gallery and you download the latest plugin, then this is the behavior you obtain. Essentially, the same engine that you saw here doing this live demo runs as a post-build step. So you compile, and then we analyze your DLL, and then we produce this list of warnings. Then you go and you essentially double-click as you are used to do. And you go there or you go there. And then you get this one. Okay, so I think I'm running over time, so I can take other questions offline. Oh, one last question. Okay, so the question is there a list of all the errors you can detect? Is it documented? Okay, actually, yes. So we have some options. So I didn't show here, but let's say in our integration with the VS Gallery, when you run with the post-build step, essentially we have you can choose which errors you want to see. So non-null pointer, buffer overrun, arithmetic overflows. We do things. Or enums, we do all this kind of stuff. And we check contracts. Remember, we are doing contracts. So whenever your method is a precondition, we checked the precondition before calling this guy. And when he has a postcondition, then at the exit of the method, we check the postcondition. And when you have an assert, we try to check the assert. So we do this kind of stuff. I'm sorry, I can take other questions offline, but I think now I really spent too much time. You know, Italians speak a lot. Thank you.